Hey, John here. Let's talk about what valgrind is, okay? Valgrind is a suite of tools for debugging and profiling programs. All right? What do? You run it, and then you run you say valgrind space, and then the name of your program in the simplest of terms, right? And if your program has command line arguments, they go over here, all right? So you just run your program as you would normally do, but you put the word valgrind in front of it, okay? Now, blah, 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 blah. I don't even know what most of this thing does. I use it in its simplest form, which is what I'm going to show you. A hugely valuable tool. All you need to do is know about one or two things, and makes your life a lot easier. So let's look at a program that I wrote called mystack1.cc. Let's see how long it takes us to figure out what's wrong with this program. What does it do? As the name suggests, it's going to build a stack. And it's going to build a stack out of a singly linked list. And each one of the elements in the list that goes into the stack is going to be represented by this struct node right here, okay? What each element has is an integer value and a pointer to the next node in the singly linked list. If I construct this node, I'm going to pass it the value that it should go into the node, and I'm going to give it a next pointer that's going to point to the next node in the linked list that represents the stack. You know, if you think about it, if you're going to build a stack using a linked list, the head of the list can be the top of the stack. Every time you add a node, you only really have to add them to the head of the list. Every time you pop an element out of a stack, all you need to do is remove a node from the head of the list. That's all you got to do. And those are the easiest operations to do on a singly linked list. So it seems to be like a good idea. All right, so let's do this. Now we have this class called myStack. This is going to represent the stack as a whole. I have a constructor that has no reason to do anything really, so I just stub it out. You could put default in there or whatever. I have a destructor that's going to clear the stack, right? Here's the clear function over here, and as my doc says, it's going to delete all the elements of the stack. If I don't clear it, when I delete my myStack, all those nodes in the linked list will be lying around in memory, and I'll be losing memory. We call that a memory leak. And that is what valgrind is going to help us find, okay? So this actually helps us by not having memory leaks when we destruct our stack, right? Or more accurately, the fact that I call it up here is why we won't have a leak caused by destructing the stack anyway. What else do we have? We have a function called size that returns this variable here. And we have an empty one that says the size is 0. So this is going to return true, as I say, when the stack is empty, right? Size is going to be, we're going to keep track of the number of elements that are in the stack as we go, so we can ask what they are. That's why this not empty thingy will work, okay? It's not empty provided that size is not 0, okay? How do I look at the top element in the stack? Okay, I got a function that will return a reference to the integer value that's at the top of the stack. Okay, I've got an assertion in here because stacks, like in an algebraic expression, if you divide something by 0, that's not defined. It's just not possible to do that. It's illegal. It's undefined. It doesn't make sense. You just can't. It's just not allowed. So I'm going to use an assertion for this. If you don't know how assertions work, I'll put a link to a video on this subject in the description below. This one on YouTube, okay? But that's why I assert this thing, all right? The short of it is this thing has to be, the head pointer has to have a non-null value in it in order to be able to use this expression here and get the value out of the head node. So this will kill my program if it doesn't have one, all right? It's a C++, so one could argue I should have thrown an exception in here or something like that instead. But I'm lazy. I'm going to just assert that the head value is not null. Okay, and then I'm going to return a value. What do we do for a push? Well, I'm going to say, remember, I'm going to create an element over here, and I'm going to store the value that I want to push into my stack, into that new element, the new node that goes in my linked list. And when I create this new node, I'm going to give it the value, and I'm also going to give it the current address of the head node. Okay, the node on the top of the stack. Why? Because when I create this new node, this is going to become the new head node. It's going to become the new top of the stack. And its next pointer, I want to point to the old top of the stack, which will become then the second element in the stack. So this is what's going to maintain my stack order. The fact that when I push things in there, the new one points to the old one, and the new head, which represents the top of the stack, points to my new node. All right. If I push a value in there, I count it. Remember how many there are in there. Otherwise, if I ask how many nodes are in that, how many elements are in that stack, if I pushed a million things in there, I don't want to have to go through the entire linked list and count them all in order to figure out there's a million. So as an efficiency move, I'm going to just count here and remember how many there are. How do I pop stuff out of the stack? Well, first of all, again, I assert that the stack is not already empty, because it's mechanically impossible and illegal to pop things off an empty stack. Now, your application might simply ignore the case when there is nothing in the stack to pop. Whatever you want to do, that's fine. But I'm going to go ahead and be strict here and say if anybody ever calls pop on an empty stack, their entire program will die. How do we pop a stack? What we do is we take the head pointer that's currently pointing to the top of the stack, and we set it so that it's now pointing to the second element in the stack, right? The second element in the linked list is the first element's next pointer. It points at element number 2, okay? So once I've done this and I move the head pointer over to that second node, the node is no longer in the linked list. I remember that I've removed one, and I go on my merry way, okay? That is how you pop something out of a stack. Here's where I remember where the size is, and I initialize it to 0. That's why there's nothing to do in the constructor, by the way. And here is my head node pointer, and I initialize it to the null pointer, which represents I have an empty stack. 0 elements and a null pointer in the head. That's an empty stack, okay? Here's my main function. What am I going to do? I'm going to create a stack. I'm going to push a bunch of stuff into the stack, and then I'm going to say, while the stack is not empty, I'm going to print out the element on the top of the stack, followed by a space, and then I'm going to remove that top element from the stack, and I'm going to just go round and round and around. This is going to just pop everything out of the stack and print it out. So if I push in 1, 12, 72, 72, 22, 4, and I pop them all back out, this should print 4, 22, 72, 72, 12, and 1, right? If they pop out in the opposite order that they were pushed in, right? After that, I'll print a carriage return so that my output's not screwing up the whole screen, and I go on my merry way, okay? Let's go ahead and compile this. Let's go ahead and run it. I'm sure you've already noticed the problem by now that's in that code, right? There's definitely a problem with that code. Yet it works. A naive programmer would say it works absolutely perfect. Right? I pushed in 1, 12, 72, 72, 22, 4, and I popped out 4, 22, 72, 72, 12, 1. What could possibly be wrong with this program? Well, let's run it through valgrind, okay? Here we go. What does it say? Well, I run it. It says some blah, 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 written by this guy, and it does this, that, and the other thing, and it says valgrind is executing this command right here, and then as the command runs, it prints this stuff out. It's perfect. I'm a genius. And then it says some stuff down here that I'm so smart I'm going to ignore, go on my merry way, deliver this product to a user, have it fail someday, and I'll end up, with a whole bunch of problems and a big black eye in the public press, right? Yeah, because I didn't bother to read this. What does this mean? In use when the program exit, I got 96 bytes in 6 blocks, whatever that means. That's amount of memory that's in the heap of my program that was running. Total heap usage, 8 allocations, 2 frees, and this is the total number of bytes that were allocated while the program was running. Well, if I allocated 8 things and I only freed 2 of them, one could theorize that there's probably a problem. Notice the difference is 6. And this says, in use at exit a program, a bunch of bytes in 6 blocks. 6 things should have been freed up, but they weren't. Leak summary. My memory is leaking. I lost 16 bytes in 1 block and another 80 bytes in 5 more blocks, and blah, 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 blah. Okay? Bunch of stuff about badness. Rerun with link check equals full to see the details of the linked memory. Okay? Again, if you're a fool and you see your right output and you ignore all these warnings down here, then you have already failed. So if I want to run, this is the one option out of that bazillion that we saw on the man page that I want to use. Run it again. What happens? Well, it starts out the same way. I'm running my stack. I got my perfect output. I'm a genius. I wrote my code. It worked on the first try. And then we read the summary. This is the same thing it said before. Down here, this is all the same thing it said before. But now we have this one more thing in here. So many things in one block is definitely lost in loss record 6 out of 6. It's not a good record. And it says at something when I was calling the new operator in this library, which, God knows where that comes. It's part of the operating system, right? But that was called by my stack push that takes an integer argument in mystack1.cc on line 43. Now we can see something going on here. That itself was also called, or the most recent time it was called, was from main on line 71 in mystack.cc. All right, so let's go ahead and look and see what's going on here. 71 called 43, right? So 71 was the line in main that it was griping about. That's the last time I called push, right? And it says that 43 did a new. Okay, is there anything wrong there? No. This is what's telling you I did a new on something that I never did a delete on. It should be obvious at this point that if I'm going to push something into the stack and I'm going to call new, after I'm done popping it out, it would be wise to delete it. All right? So my program appears to work okay. I'm not going to edit this file. I just have the other copy of it. To put a delete in here, I got to remember where the old top of the stack was, because I'm going to update the head node pointer to point to that second node, right? But once I've done that, I forgot where the old top was. So I got to save the old top pointer in the temporary variable called P. Move the head top of the list to the second element in the linked list. When all that's done, I can delete the old top of the stack. And again, count it and go on my merry way. All right, so let's make sure it's compiled. Yes, it is. We can run it. Of course, it still works, right? It appears to be okay. Let's make sure that we're not leaking any memory. Oops. It says it can't find it because it didn't tell it where to look, which is in the current directory. That's what that means, right? So now it runs. It says, okay, we're looking good. I ran my stack. Here's the output when it ran. And then down here it says I had 8 allocations, 8 frees. I allocated this much stuff out of the heap while the program was running. Everything's fine. No, all blocks saying no leaks are possible. As long as it says this, that's great. This is the correct program. All right. Now you might say, oh, who cares? The first one worked. Why bother wasting our time? Well, what really would go awry? Right? Why would that be a problem, right? Well, let's say I did this, right? This is the first one. It still has the bug in here, right? Let's go up and double check, right? The pop, we don't have the delete in here, right? So let's say you're running a program that, it's like a server and it stays running for like a bazillion years, right? So for I equal, well, actually, we don't need to do that at all. We could just say while. Let's say you write a program that has an infinite loop. It's like a server, right? And, this is super trivial, but, a very complicated, deeply nested bunch of calls and stuff. You could effectively be doing things like where you push a value into your stack, then you do a bunch of processing in here, and then you want to pop it back out. Okay? So let's say this is part of your normal operation, and your program is never supposed to end. Okay? Let's go ahead and put this at the bottom of the file. Like this. Then we'll fill up the stack with a bunch of stuff, print it out like we did before, and then we're going to go into this super duper main processing loop. What's going to happen in here? Well, in theory, the program could run for eons, and it would just be fine. It would just never, ever end. Except every time we call pop, we're not really removing that thingy out of the memory. If we run this program, it won't take long. Okay? Doo-dee-doo-dee-doo. You sit there going along, everything's fine, you know. You go home for dinner or whatever, you go and grab yourself a nice cup of coffee, and then later on, around 4 in the morning, you know, you get a phone call and says, you know, your program croaked. You say, no, it can't possibly be my fault because I tested my code. I'm perfect. So what happened? It's just running. I was just, killed. Thank you. Okay, and let's say that took, 12 hours to happen, all right, 3 days or 6 months. I got a great story for you sometime. I had a job once where I wrote some code, and it was a very low-level device driver, and only about once every 3 to 6 months did it fail, okay? It turned out that my code was fine. I was using a library function. It wasn't leaking memory per se, but there was a memory corruption problem affiliated with it in a system library. How should we trust these things, right? and it was sort of like this. It takes a very long time for the thing to fail, right? And when it did, I don't know what's wrong. And then we got to wait another 6 months to debug it again. Oh, that was difficult, right? You need to use all these kinds of tools on your apps to figure these things out. It turns out that my problem was not fixable with valgrind. Otherwise, I would have found it sooner. But it was a tricky one. Point is, some of these are really difficult. But let's not make all of life's problems difficult, right? So let's see what happens if we valgrind it when we have this giant endless loop that's just wasting memory. And that's why it's killed, by the way. It's killed because it ran out of memory. If you run it with valgrind and it dies, you're gonna get a lot of information about why it died. Now, of course, valgrind does take a little bit of overhead to run, so it might take a little longer this time before it gets to the point where it dies. Now, we don't even need to wait for it to end, right? We can just let it go for a while. So I just let it run for a few seconds and hit Control-C, right? And it's still going to terminate, and it will still do the analysis. It stopped, and look at this. How many bytes and this many blocks were in use when the program stopped running. Look at all that's 1.5 gigabytes of memory. Okay? That's a lot of memory. Does it make sense that my program should ever use that much memory? I mean, yeah, maybe it does. Maybe it could, right? And in fact, it took valgrind an awful long time to figure out how to stop itself with all that memory being wasted and all those statistics. So what does this say here? It definitely lost all that memory and this many blocks, and it says what? Where does it say the total number of allocations was probably like a gazillion? I would have to run the leak check full to get more detail as it goes. Let's go ahead and run that too. And this, remember, is the endless loop version. So what is this thing going to do? Well, it's going to cook for a while. When you're bored of waiting, you might hit Control-C to kill your program. And now the thing about hitting Control-C on a running program, it's going to stop wherever it is. And it might actually be in a situation where it is okay to be using a lot of memory when your program's running. Because remember, I just stopped it in the middle of doing something. My program never finished. It never cleaned up after itself. It probably is going to be using something at the time I killed it. But look and see what it says down here. In use at exit is an awful lot of memory. Total heap usage is a whole bunch of allocations. 11 million allocations and only 2 frees. Now that might not be wrong. Again, remember, I stopped it while it was going. But since I understand the nature of my program, these should remain relatively balanced over the course of time. So this, to me, right there, this should be obvious that there's something wrong with my program. Not sure exactly what, but let's see what's going on down here. All right, it says, well, I definitely lost 6 of 8 things. All right, now just because I killed it, remember, and it didn't have a chance to clean up itself, that's absolutely critical to add that into your reasoning here. It could have cleaned up, all the stuff that's in use right now. However, if it definitely lost some data That means that valgrind was able to figure out that you did a new on something, and you no longer have the pointer that points to it. That's why valgrind takes a little bit of overhead while it's running. Think about that. What does the program do when I forget to delete it? It takes the head pointer and it no longer points to the top of the linked list. It simply moves the pointer over to the second element in that linked list. Nothing in the system anymore is pointing to the old top of the stack node. And valgrind figured that out. It knows that I did a new, and it knows that there are no pointers anywhere in my entire program that point to that thing. Therefore, it's not possible for me to be able to clean that up, even though I killed the program early. I can tell you I can't clean this up because I definitely lost track of it due to my flawed implementation of my code, all right? So even if you don't wait for it to end, it'll tell you all this great stuff, okay? When you're done with a program, just simply run it through valgrind, okay? Make sure it says what it said the last time we did this on my stack 2, which is the correct version, right? It starts, it runs, it ends, it absolutely says everything's great, okay? Let's modify my stack 2, just for thorough, just to complete this thought here. What if I do this? Well, we do the same thing I did before, but on a program that doesn't leak memory when it runs, okay? And here, what if I do a push for, and then I have my, my super awesome profit-generating business stuff in there. And then I say pop, what do I say? S push, right? Stack push, and then stack pop like this. What if I run this and I hit Control C, right? Because, I'm waving my hands and making things up in this discussion. No, I'm not. So if we go in here and we run my stack 2 now, okay, because I just put the endless loop in there, it's going to go, it's going to print it out. Now it's going into its endless loop, okay? Let's let it cook for a minute. It is an endless loop, so it'll never finish on its own. But if I hit Control C now, okay, I pulled the rug out from under its feet, and valgrind says, well, I'll do the best I can, right? So what happened? I killed the program, and it tells me all kinds of stuff about it, right? Here's where it was when it died. It was in the middle of pushing something. Okay, great. In use at exit right now, I have 16 bytes of memory in one block. Well, that's a lot better than a gazillion, right? So it suggests I'm not using a whole lot of memory when I killed it. Total heap usage, I allocated 10 million and change, and I freed 10 million and change, right? I have one more allocation than I do free. If we look at the code in the push routine, I bet push has just done the new on this line 43, and it has not yet gotten to the point where it returns from the subroutine. Okay, so that's probably why there's one more allocation than free. What else do we got? I got 16 bytes in one block is definitely lost. Okay, why would that be? That makes me mildly nervous. It's definitely lost. You know why? Because in line 43, I'll bet anything is after the new. I probably haven't stored it anywhere yet. Where's line 43? So what's probably happened is it had done the new, and it has not yet assigned it to the head list pointer over here. It probably died before it finished this assignment. That's why it lost one. Okay, I'm guessing. Yeah, I'm guessing. But due to the nature of this program, this is behaving very well. Okay, this is a sign of a properly running program, even though I killed it. Okay, so this is the kind of stuff you can get from valgrind. It's enormously useful. You should use it whenever you're doing anything that uses any pointers, anywhere in any program, especially if you're a student. All right, because it's easy to make simple little mistakes, and then the next thing you know, you think your program's fine, and your teacher's secretly grading your assignments by running them all through valgrind, and you don't even know you have a problem because, like I showed you up front, these programs all generate the perfect and correct output. It's just one of them didn't do it correctly. So use valgrind on your code so you always know everything's okay. All right? Thanks for watching. See you next time.